The aim of this lesson is to have a look at some circle geometry past paper questions, but continuing our theme of slightly unusual questions, some things that look a bit different or work a bit different, or you have to be thinking of something a little bit different to normal. So we have a diagram. We have OAB is a sector of a circle with center O and radius R. The point C on OB is such that angle ACO is a right angle. Angle AOB is alpha radians and is such that AC divides the sector into two regions of equal area. Show that sine alpha cos alpha equals half alpha. Okay, right. So that is an unusual show that question, but we can still use exactly the same understanding and approaches that we would normally for these questions. Okay, so we take a relationship that we find in the equation and we work with it. So they tell us that this line AC divides these two into equal areas. Well, we have a triangle, we can do area of a triangle, that's not a problem. Area of this funny shape is, who knows? But area of this triangle being equal to that means area of the triangle is half of the sector. So we do have the relationship of area of triangle AOC equals 1/2 the area of sector OAB. So if we can then come up with two area formulas, we can equate them and we can then, in theory, show that sine alpha cos alpha equals half alpha. So area of triangle AOC. So we have a beautiful right angle triangle. So we can just use our basic and our straightforward half base times height. But we have neither the base nor the height. So how are we going to do that? Well, a clue there, we have sines and coses going on and we have a hypotenuse. So if we just take our little triangle out, here's our alpha, here's our R, OAC. So our base is OC and our height is AC. And we would need both of those in order to do the area of our triangle. So let's start with our base. We know that OC is adjacent to alpha. Adjacent and hypotenuse, we know that, sorry, not OC equals, but cos alpha is going to equal adjacent OC over hypotenuse R. So OC is going to equal R cos alpha. Remember, we always put the R at the beginning, so that is multiplied. Similar type of thing for AC, only now it will be opposite and hypotenuse, so sine alpha equals AC over R, AC equals R sine alpha. So we now have, we think through it, area of a triangle, half base times height. Area of the sector, 1/2 R squared theta. So area of our triangle, we have 1/2 base is OC, R cos alpha times height, R sine alpha, equals 1/2 times the area of sector OAB, that is 1/2 R squared. Theta in this case is alpha, because remember we don't want to write down those formulas. So 1/2 R squared alpha. Now this is looking rather familiar to what we were aiming for. So multiplying both sides by 2, clearing the fraction, and then we can rearrange a bit to make things look nicer this side. So we would have R squared sine alpha cos alpha equals 1/2 R squared alpha. If there's an R squared on both sides, then the coefficients of the R squareds must be equal. So therefore, sine alpha cos alpha equals 1/2 alpha, shown. So just because it's slightly different and just because we're doing more calculations for our show that, it still responds in exactly the same way to building the relationships and then working through the calculations. There is a part 2 for this question. It is given that the solution of the equation in part 1 is alpha equals 0.9477, correct to 4 decimal places. So now we've got the value of alpha. Find the ratio perimeter of region OAC to perimeter of region ACB. Giving your answer in the form k is to 1, where k is given correct to 1 decimal place. So we need the perimeter of OAC and the perimeter of ACB. So the perimeter of OAC would be R plus our R cos alpha and our R sin alpha. So perimeter OAC equals R plus R sine, instead of alpha we have 0.9477 plus R cos 0.9477. So 1 plus sine 0.9477 plus cos 0.9477. When we add those three together, we get 2.3956 times R. Because remember, when we have an R on its own, there's a 1 hiding there. So that's our perimeter for OAC. Working to more decimal places than our final answer will be. If we look now at ACB, a funky shape, the perimeter is our AC, same as we worked with in part 1. BC, we haven't worked with that, but we've worked with OC, right? And if you take OC away from the full R, then you're left with BC, so we can get BC. And then we have our arc AB. So the perimeter of ACB equals R sine 0.9477, there's our AC, plus BC, R minus R cos 0.9477, plus, how do we do? The arc length is R theta. So R times 0.9477. So again, we've now got on our calculators, sine 0.9477 plus 1, minus cos 0.9477 plus 0.9477. So we're taking those coefficients of R to combine them all, and we get 2.1762 R. So we've now got the perimeter of each shape. We now need to make our ratio. So the ratio is 2.3956 R to 2.1762 R. Fantastic. Putting it into simplest form, that R disappears. Okay, they wanted K is to 1. So we're going to divide through by 2.1762, and we get, as expected, 1 on the right-hand side. 2.3956 divided by 2.1762, then to 1 decimal place. So just 1.1. So our final ratio is 1.1 to 1. So again, we're just working systematically through using all the information in the question. And here is the really unusual piece of this question. The really, really one. Find angle AOB in degrees. So we've got 0.9477 radians. And in this question, they actually want us to convert to degrees. But now I've been spending all my time teaching you never combine, never convert, work in one, work in the other. So now you get in the exam and think, oh, whoops. But you do know how to do this. Because you know that 180 degrees equals pi radians, right? So 1 radian equals 180 over pi degrees. So we take our radians here and we times by 180 over pi. 0.9477 degrees. 180 over pi times 0.9477. That gives us a lovely and straightforward 54.3 degrees. So there is no need to now freak out and go and learn how to convert. You've got an understanding of that relationship between radians and degrees because you know how the two of them work. So what is important is that you can trust in your knowledge and you can use the information that you have in order to then go and work with it in questions, even if it's a slightly out of context from what you would normally be working with. Okay. We have happy people, so let us carry on. The next question. So in this question, it's calling on some knowledge that I'm hoping that you haven't forgotten from your IG days. We have a diagram with a whole lot of information. Diagram shows a sector of a circle with center O and radius 20 centimeters. A circle with center C and radius X centimeter lies within the sector and touches it at P, Q, and R. Angle POR equals 1.2 radians. Show that X equals 7.218, correct to 3 decimal places. Right. So, X. X is out there in the middle of nowhere doing nothing, and it's like, okay, well, how do we relate that to anything? But if we think about this radius, right? O to the circumference of 20 centimeters, when that radius goes everywhere through this whole sector. So that tells us that OQ of 20, right? Because this is a 20 centimeters, which means that X is going to equal 20 minus OC. Because this piece here, we take it away from a 20, then we're sorted. But now how do we get OC? So if we draw in a nice little OC line, we now know this angle would be exactly in half because we got a beautiful circle going on, so a 0.6. How does that help us get X? It's that wonderful relationship of a tangent and a radius. If this line is touching the circle, the line is forming a tangent to the circle. And a tangent to the circle always meets a radius at right angles, which means that if we put a line in here, this is a right angle. On top of that, this is a radius, this is a radius, this is X. And now all of a sudden, we have an angle, an X, and the OC that we're interested all in one place. Okay, so we can get OC in terms of X. And then if OC has X's, that's fantastic because we can solve for X. So for OC, we know that we have an opposite and a hypotenuse here is OC. So sine 0.6 equals X over OC. Remember, we don't use HOA when we're doing these. We use the letters that really describe the line we're working with. So OC would then equal X over sine 0.6. And if we've got then a value for OC, therefore X equals 20 minus X over sine 0.6. So clearing that fraction, X sine 0.6, always multiply at the front of the trig function, equals 20 sine 0.6 minus X, we've cleared the fraction. So if we now then x times sine 0.6 plus 1x, that gives us then a 1.5646 x's, and that's equal to 20 times sine 0.6, which gives us 11.29. Clearing our 1.5646 by division, we then get x equals 7.21772. Now, I like to give a few extra places here because they want us to show that x is correct at 3 decimal places. So I want to show them that I did get the correct longer answer that then rounds to the same answer that they got. So x equals 7.218 to 3 decimal places. So don't forget, when you are looking for your right angle triangles, if you're dealing with circles in particular, if you have a line that is a tangent to your circle, then it's meeting your radius at a right angle. So you have a beautiful right angle triangle that you can then create to use for your SOHCAHTOA. Part 2 for this question asks to find the total area of the 3 parts of the sector lying outside the circle with center C. No shading in this question, but they're asking us for the area of these 3 pieces. So how do we do those? Well, if we have the whole area of the sector and we take away that circle, then we'd be left with those 3 pieces. So area outside circle equals area of the sector minus area of the circle. Area of the sector, remember we're not using any formulas in our working, we're just applying them. Half r squared theta, so 1/2. R is 20, theta is 1.2. So 1/2 20 squared times 1.2 minus the area of a circle, pi r squared, pi times 7.21772, because whenever you use a number in a calculation, you want to go back a step. You don't want to use rounded figures. Always use an unrounded figure so that your answer is as accurate as possible. And 1 time 1 calculation, our calculator can do that quite nicely and happily. So we plug it all in and our final answer is 76.3 centimeters squared. Last one. Find the perimeter of the region OPSR bounded by the arc PSR and the lines OP and OR. So now we are looking at this shape here. I think we need a different color because we're getting very blue and we're running out of visibility. So we want this piece here. So OR, we can see already, that lies in our helpful triangle from the beginning. We've got our value for X, 7.218, and OR is our adjacent of our 0.6. So we can get OR equals OP. The fun thing is, how do we get this arc? Because for this arc, we're going to need the angle in this sector. So we get nice and clever again here, because it's every radius that meets every tangent at 90 degrees. So this here is also at 90 degrees. So we've now got a quadrilateral, have we not? We've got pi over 2 plus pi over 2 plus 1.2 plus our angle of interest. Oh, we can't use x, they've used x, let's use a for angle. And angles in a quadrilateral sum to 2 pi. So that angle of interest, 2 pi equals pi plus 1.2 plus A. So A equals pi minus 1.2. Now we have our angle. So those things that you did at IG Maths, yes, you can forget a lot of them. Don't tell anybody I said you that. But you do need to remember some of them because they do come in so very useful. Your geometry at IG Maths is not something to completely throw away. So we said that OP equals OR. So for OP and OR, we know that it was tan of 0.6 working in our little triangle equals x 7.21772 over, we can use OR. So OR equals 7.21772 over tan 0.6. Evaluate everything one time, 10.55. So OP and OR are 10.55. For our arc, let's just put it here. We said that angle equals 2 pi minus pi over 2 plus pi over 2 plus 1.2. So the angle equals pi minus 1.2. So for arc PSR, we then have arc PSR equals R 7.21772 times the angle pi minus 1.2, and that gives us 14.01. So now we've got everything we need to do the perimeter. Equals 2 times 10.55 plus 14.01, and when we combine that all together, we end up with 35.1 centimeters. The perimeter of that very funny shape that had a pointy bit with a scoopy bit at the bottom of our diagram is 35.1 centimeters. So again, it's really important that when you approach a question like this, you take that time to think about different relationships that you could be using in order to get your very helpful right angle triangles that then you can use for SOHCAHTOA for all sorts of different things within your question.